In our previous lesson, we spent a good bit of time discussing how algebra and combinatorics are related by talking about the binomial theorem, which helps us expand binomials, and its connection to Pascal's triangle. We also developed a formula for the elements of Pascal's triangle that involved the factorial function. In this lesson, I want us to take this material one step further to see how we can actually use this information to count things known as permutations and combinations. So let's start with the idea of a permutation by looking at its definition. A permutation is simply an arrangement of a set of items in a particular order. Now, that definition might not be that helpful or enlightening to you, so let me look at a basic example to help solidify the idea of a permutation from a mathematical perspective. Here's the example I want us to look at. Write down all the permutations of the letters A, B, and C. Now, what are we being asked to do? Well, we're asked to write down all the possible arrangements of these three letters in a particular order. So the permutations of the letters A, B, and C are the following. ABC, that's one permutation. ACB, BAC, BCA, CAB, and CBA. Now, that's all the ways that I could order those three letters. And I want you to notice that the order matters with these permutations. The order in which I place the A, the B, and the C does matter whenever you're writing down permutations. And that's going to be a pivotal fact as we continue talking in this lesson about permutations and combinations. Now, how many permutations did we just find, by the way? Well, if you count those sequences of letters that I just shared with you, there were 6 of them. And now, one question you and I should ask, which is actually a very good question, is where did that 6 come from? I mean, admittedly, I could have just counted 1, 2, 3, 4, 5, 6. But as I've already shared with you in the past, combinatorics is about trying to think sort of intelligently about how to count so that we can see where the 6 of these permutations actually came from. So think with me for just a moment about how we built the permutations that we just created. Imagine, before I wrote down any of those 6 permutations, that I simply wrote down 3 blank lines. And I imagine putting one of the 3 letters in each of these blanks. Let's say we start with the first blank. We need to put one of the letters A, B, or C into that first blank. How many different choices do I have for filling in that blank? Well, there are 3, because I could have put in the A, or I could have put in the B, or I could have put in the C to get this permutation started. So I have 3 choices for that letter. Let's just pick one of them to start filling in this permutation. Let's say I picked B. So I place the B in as the first letter of this particular permutation. Next, I need to fill in the second blank. Now, an important question comes up, which is, how many choices do I have for filling in that second blank? Well, the answer is not 3, because I no longer have 3 letters to choose from. The B in this example has already been used. So in fact, to fill in the second blank, I only have 2 choices. I either have to use the A or the C if you're following along with this one example. So the B is no longer used, and so this second blank has 2 choices for what to put into it. And now let's say, for fun, we just put the C into that second blank. Now, once I've done that, I need to fill in the third blank to complete the permutation. Well, how many choices do I have? Well, I have 1 choice, if you want to think of it that way. I have to use the A. I know that for some folks, the idea of a choice here is a little bit forced. In other words, I have to put the A in, so I really don't have any choice. That's what some people like to say. But in fact, that's not the way to think of it. You should imagine what we're really doing is asking, how many different letters could I put into that blank? And then the answer is just 1 because we have to use that letter A. Now, once I've done that permutation building, in this case I built B, C, A, we can step back now and ask ourselves, how many ways could I have built different permutations? At the first stage, which was filling in the first blank, I had 3 choices for what letter to put in as the starting letter. And then at the second stage, I had 2 choices for the letter to put into the second position, and then I had only 1 choice for what the last letter could be. And now you have to ask this question, well, what do you do with this 3, this 2, and this 1? And with that question comes a very important mathematical principle in combinatorics. It's known as the multiplication principle. And I'm going to refer to this principle often, both in this lesson and in the next lesson. So let me share it with you and then try to make sure it makes sense. The multiplication principle says this. Suppose you have a procedure that can be broken into m successive stages, and the first stage has n1 different possibilities for it, and the second stage has n2 possibilities, and so on, until the last stage has what we might call n sub m different possibilities for that last stage. If the number of possibilities at each stage is independent of the choices made in the previous stages, and if all the final outcomes are different from one another, then the total number of outcomes for completing the whole procedure is exactly the product n1 times n2 times ... n sub m. So the point is this, if you're doing a full procedure that has several little stages in it, as long as the stages are basically independent of one another, and you know how many ways to complete each stage, then the total number of ways to do everything is just the product of the number of ways to handle each stage. And that's why it's called the multiplication principle, because you're just taking a product at the very end. So when we build these permutations in stages, we started with blank 1, and then the second blank, and then the third blank. It turns out that by the multiplication principle, the total number of different permutations that I could build was exactly 3 times 2 times 1, which is equal to 6. And that's where that 6 came from in terms of trying to find all the permutations of the letters A, B, and C. Now, if you think back to the previous lesson for just a second, something else should strike you as a relationship between what we're talking about here and what we talked about there. Namely, by this multiplication principle, in this example, 3 times 2 times 1 is the same as 3 factorial. So the number of 3-letter permutations is exactly 3 factorial. Now, is it a coincidence that the number of 3-letter permutations is exactly 3 factorial? I think not. It's exactly going to be that kind of formula every time we try to build these kinds of permutations. If you think about it, the blank filling procedure that I had you do would always give you a factorial. Try 4 letters just for a moment. Take A, B, C, and D, and now write down all the permutations you can write down. Well, you know, this is going to get kind of tedious after a while to write them all down and then count them 1, 2, 3, 4, and so on. So let's just think about the procedure for building the 4-letter permutations first, and maybe we can actually get the formula to pop out. So start with 4 blanks. How many ways can you fill in the first blank? Well, it's 4 because you've got 4 letters to start with. Then, once you pick one of those letters and place it in the first blank, how many choices do you have for filling in the second blank? Well, it's 3 because you have 3 letters still in your hands, if you will, that you haven't put down in the blanks yet. So the number of ways to fill in the second blank is 3. Then the next blank has 2 possibilities, and the last blank has 1 possibility. Whatever letter is left has to go in the last blank. So by the multiplication principle, the total number of ways to complete this step-by-step process of building 4-letter permutations is 4 times 3 times 2 times 1, which is just 4 factorial. And so there are 4 factorial permutations of 4 letters, which is the same as saying there are 24 permutations with 4 letters. And we could keep doing this, we won't, but we could keep doing this with more and more letters and more blanks if we wished. But the point is, we now see the pattern. And here's the fact about permutations. The number of permutations which use n letters equals n factorial, and we've seen this factorial function in the previous lesson. So even if you had a really big number of letters, like you had 10 letters, and you wanted to build all the permutations out of those 10 letters, you know how many you would have to build. It would be 10 factorial, which, by the way, is 3,628,800. No matter who you are, you have to admit that's a lot of permutations. And I definitely would not want to have to write all of those down and then count them one at a time to figure out how many I had. It's more than 3 million permutations. So this formula that you use n factorial to count the number of n letter permutations is extremely helpful. Now, let's turn a corner and talk about permutations where you don't use all of the letters. So let me tell you what I mean by this. Let's look at the following example. Let's say you have 5 contestants in a competition, and you're going to give a first place, a second place, and a third place trophy to these contestants. How many different outcomes are possible for this competition? Now, the first thing I want you to notice is that the order definitely matters in this problem. Let's say, for example, that Anne, Bill, and Kathy are the top 3 people out of the 5 contestants. Notice that Anne would probably be happier if she won first place than if she won third place. And that fact that Anne would rather be in first place than in third place is enough to convince me that order definitely matters in this problem. And because order matters, it tells me that I'm definitely dealing with permutations. But I'm not interested in permutations using all 5 of the people. We only want permutations of 3 letters taken out of the 5 letters. In other words, not to be mean, but the 4th and 5th persons don't matter because we're only going to give 3 trophies. So, for example, if the people were named A, B, C, D, and E, then I would want permutations like A, E, D, which would mean A was first place, E was second place, D was third place, and B and C don't get any trophy at all. So here's the question. How many of these kinds of outcomes, these kinds of 3-letter permutations taken from 5 letters, can we build? Well, guess what? It's the same principle and the same procedure. Let's go back to this blank filling idea. Now I want 3 blanks. One's going to be first place, one will stand for second place, and one will stand for third place. And I want to be able to fill in these 3 blanks using my 5 letters A, B, C, D, and E. So I'm really only going to use 3 letters at a time. How many ways can I fill in these blanks? Well, it's a step-by-step procedure again. Let's start with how many ways we could fill in the first blank. Well, the answer is not 3. The answer for how many ways you could fill in the first blank is actually 5, because you have 5 letters to choose from for that first blank. So the first stage of this permutation building operation is going to have 5 choices. Okay? Now, let's just say for fun that we put the letter A in that first blank. Now, how many choices do I have to fill in the second blank? Well, there are 4 letters left, or 4 people left, however you want to think of the example. So the second blank would have 4 choices for what to place into that blank. Then, how many ways can I complete or fill in the last blank? Well, the answer is 3. We're assuming here that no one gets to be both first place and second place. We're going to give 1 trophy to one person and another trophy to another person. So the first blank had 5 choices, the second blank had 4 choices, and the third blank had 3 choices. So by the multiplication principle, the total number of ways to determine the first, second, and third place winners in this contest is 5 times 4 times 3, which is 60. Now, before we go past this too quickly, let me point out something. 5 times 4 times 3 should remind you of 5 times 4 times 3 times 2 times 1, which is 5 factorial. Except as I like to say it, the tail has been cut off, so to speak. You're missing the 2 times 1. But that's actually a hint that you might still be working with factorials. Let me just mention it in this way. Think of 5 times 4 times 3 as the same as 5 times 4 times 3 times 2 times 1, all divided by 2 times 1. In other words, the 2 and the 1 are going to cancel one another. But that's the same as 5 factorial over 2 factorial, which, oh, by the way, is the same as 5 factorial divided by 5 minus 3 factorial. Remember in this example, 5 was the number of people we started with, and 3 was the number of people that we were actually putting into these blanks. And this gives us the motivation then for the following mathematical fact. Let P of n comma r be the number of permutations that you can build using r letters out of a total set of n letters. In my earlier example, r was 3 and n was 5. Then P of n comma r, which is trying to count this number of permutations, is exactly n factorial divided by n minus r factorial. So in this previous example we were doing, n was 5 and r was 3. So what we just calculated was P of 5 comma 3, which is 5 factorial over 5 minus 3 factorial, or 5 factorial over 2 factorial, which is 5 times 4 times 3, which is 60. So this example proves to be a really motivating example for trying to find permutations in general. And what I'd like to do now is move us to another example to look at permutations and how to use this formula to count them. So here's the example I want us to look at. How many different 7-digit phone numbers can we write down where all of the digits are different, and I'm going to make this comment, where the phone number is even allowed to start with a 0. I realize that in most cases that would be silly, but it'll make our problem a little easier as we try to use it to help us learn about permutations. So I really want to know how many 7-digit numbers we can write down so that all of the digits are different and we're even allowing 0 to be at the front. Now, notice that the order definitely matters. If these are really phone numbers, then you definitely have to worry about the order. I mean, how many of us have accidentally switched a couple digits when you're dialing a phone and you get the wrong number? That tells me immediately that the order matters. And since the digits all have to be different, we know that we can only use each digit at most once. Okay, so we're definitely talking about permutations just like we were in the previous examples. We have 10 digits to work with, the numbers from 0 to 9. There are 10 different numbers there. And we want to build 7-digit numbers because we're trying to build these phone numbers that are 7 digits long. So it's like we're filling in 7 blanks with 10 different numbers available to us. And that means, once we've thought through that the answer to this question of how many different phone numbers we can build is exactly P of 10, 7. 10 being the size of the big set from which we're pulling the digits, and 7 being the size or the number of digits that we want to write down. It's that simple. But what is P of 10, 7? Well, according to our formula, P of 10, 7 is the same as 10 factorial divided by 10 minus 7 factorial, which is 10 factorial over 3 factorial. And now if you write it all out and do some cancellation, you'll see that's the same as 10 times 9 times 8 times 7 times 6 times 5 times 4. And if you multiply all that out, you get 604,800. So there are that many phone numbers, again allowing 0 to be the first digit if you want, where all of the numbers are different. Now, let's look at another example, again, trying to get the feeling for how these permutations work out. How many different ways can a Little League baseball coach place the kids in the 9 positions on the field if there are 11 players on his team? Now, one of the questions you have to ask with these kinds of examples is, does the order matter? And imagine we're working with very young children at this point, just to help us with the example. Well, I would contend that the order in which the children are placed on the field and the positions that they're given really does matter, that order matters. Think about it. I've actually coached Little League Baseball in the past. If there's a child having trouble catching the ball, then making that child play the role of the catcher behind home plate is not a good choice. So we're going to need to be wise about the order in which we put the children on the field, and that means I'm looking at permutations again. Now, if I put the 9 positions on the field as the 9 blanks, maybe pitcher and catcher and first base and second base and so on, and I write those 9 blanks there, and I imagine now that I'm going to put names in those blanks for where the children are going to play, then I see that this is a permutation problem, and the first blank is an 11, has 11 choices, and the second blank has 10 choices, and then 9 choices, and 8 choices, and so on. And the answer then is going to equal P of 11, 9. And P of 11, 9 is the same as 11 factorial over 2 factorial. And now if again you multiply all of that out, 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, and divide it by 2 times 1, you'll see that the final answer is 19,958,400. That's a lot of different lineups. And for those of you who've either ever played baseball or been a coach for a team, you probably didn't realize that there could be that many different lineups that could be written down based on the positions that each child plays. Now, I'd like to transition a bit and talk about a different kind of counting problem now. We've just done a few examples on permutations where the order mattered in terms of how we placed the choices that we had, but sometimes order doesn't matter when you're choosing the items. For example, if we just need to choose 3 captains for our football team, and they're all going to be the same sort of captain, if you will, then choosing A and then B and then C is the same as choosing C and then B and then A, because they're all going to be given the same sort of captain's role. So in this kind of problem, we do not want to count permutations because we don't care about the order in which we count them. So if, in fact, you did count permutations, you would be counting too many possibilities because choosing child A first and then child B is identical to choosing child B first and then child A in this example of picking 3 different captains who have the same role to play. So this kind of an example is not an example of permutations. It's something that we like to call combinations. And now let me give you the definition of a combination. A combination is a selection of a set of items in which order does not matter. So for example, how many ways could we pick 3 captains from a 10-player team? Well, the answer can be found with the following fact. Let C of n, r be the number of combinations that we can build using R letters taken out of a set of n letters or n items. Then C of n, r is equal to n factorial divided by r factorial times n minus r factorial. So let's say you go back to a sports team and it has 10 players on it, and you want to choose 3 of those players to be the captains. And again, they're all playing the same role as captain, the same idea. Then the number of ways to do that is C of 10, 3, which equals 10 factorial over 3 factorial times 7 factorial, which is the same as 10 times 9 times 8 times a 7 factorial divided by the 3 factorial times 7 factorial. And once you cancel those 7 factorials, you're left with 10 times 9 times 8 in the numerator divided by a 6, which is coming from the 3 factorial. And simplifying all of that, you get 120. And now, if you think back to our previous lesson for just a moment, you'll hopefully remember that this CNR is exactly the CN, R that we talked about in that lesson for the elements of Pascal's triangle. It was exactly that same formula, n factorial divided by r factorial times n minus r factorial. So what does that mean? Well, this is an amazing fact. The numbers that are in Pascal's triangle are exactly what we need to count combinations. That's exactly what those numbers are used for. In fact, in some sense, that's what Pascal was trying to count when he built that triangle, was these kinds of combinations. So this is a really nice connection now between the binomial theorem and Pascal's triangle, and now these really nice counting questions, which we call combinations. Now, I'd like to suggest that we move forward with another example then, and use this formula for C of n comma r to do this example. We have a set of 6 books that I want to read during my summer vacation, but I only am going to have time to read 4 of them. So my question is, how many different ways can I choose the 4 books out of the 6 books that I have to take on my trip? Now, notice something, and again, I was saying this earlier, you have to ask this question: does the order matter? If the order does matter, you're dealing with permutations. If the order does not matter, you're dealing with combinations. Now think of this. I have 6 books in front of me. I just need to pick 4 of them. It doesn't matter to me in which order I pick them. I'm not worried about which one I read first and which one I read last. I simply want to pick 4 of them that I'm then going to put in my car to take on my summer vacation. So the order does not matter in this problem. And that means I have a combinations problem, not a permutations problem. And so the total number of different ways I can select these 4 books out of my total of 6 books is exactly C of 6 comma 4, which is 6 factorial over 4 factorial times 2 factorial. And if you simplify that again with the factorials, you're going to see that the numerator just becomes 6 times 5, all divided by a 2. That's if you peel off a 6 and a 5 from the 6 factorial and then let the 4 factorials cancel with one another. The point is, the final result for C of 6 comma 4 is 15. So let's now interpret that number. That's telling me that there are 15 different collections of 4 books that I can choose out of my 6 books in order to take on my summer vacation and read. And again, I don't care what order I pick them from, or the order in which I pick them. I only wanted to select them. So 15 is the total number of different ways to take those 4 books onto my trip. Now, you might be saying, hey, that sounded a lot like a permutation problem to me, actually, and it's not a combinations problem. Well, let me make a couple comments. First of all, a lot of students who are dealing with permutations and combinations for the first time say the same sort of thing. It takes a while, it takes some practice to be able to see the difference between the two. Now, in this particular example, let me just say a couple things. First, when I throw those 4 books into, let's say, my book bag or my suitcase or something like that, do I care about the order in which I actually throw them into that bag or gently place them into that bag? I don't want to break my books or ruin them. Of course, I don't care about the order in which they sit in my suitcase. And that is a hint that this is a combinations question and not a permutations question. Now, there's another comment I can make about the example, and that is, I actually could turn the problem into a permutations problem, and maybe I'll share that with you now, because then maybe you can see the difference between combinations and permutations a little better. Here's a permutations version of the same problem. So now I would care about the order. If you had 6 books and you wanted to put 4 of those books on a bookshelf in order on the shelf, how many different ways could you arrange those 4 books on to the shelf in your room? Well, that question, because it's asking for arrangements of the books on a shelf, would be a permutations problem, because the order that the books are on the shelf does matter. Different orders are going to give you different permutations. And at that point then, the answer to the question would have been P of 6 comma 4, not C of 6 comma 4. And by the way, P of 6 comma 4 is much larger. It's 360 rather than C of 6 comma 4, which is only 15. Now, let me move to one last quick example as we try to look at this difference between permutations and combinations, and then we'll close out our lesson. For summer camp, you're allowed to choose 4 or 5 cabin mates from a list of 12 other campers. How many ways can you do this? Well, this problem actually needs to be broken into 2 smaller problems. First, What if you wanted only 4 cabin mates? Well, does the order matter in which you actually pick these cabin mates? That's an important question that you need to ask. Does the order of the 4 cabin mates you choose matter? Well, the answer is no, because you're just going to get thrown into the cabin together. So it's not like you're worried about any sort of ordering. And that means this is a combinations question. And the number of ways to choose 4 people out of 12 is just C of 12, 4. But what if you wanted to have 5 cabin mates instead? Remember, the question asked if you wanted to have 4 or 5. Well, if you go back and start from scratch and choose 5 people out of the 12, then the number of ways of doing that is C of 12, 5. Now, in this case, you're not doing things in stages with the multiplication principle. You're actually thinking of 2 totally different problems. What if I wanted 4 cabin mates? Or what if I wanted 5 cabin mates? And that means that the answer to this question is actually C of 12, 4 plus C of 12, 5. And when you take that sum, that will give you the total number of ways to choose those cabin mates. C of 12, 4 plus C of 12, 5 turns out to be 1,287 different possible sets of cabin mates that you could have. Well, we've spent a good bit of this lesson now talking about permutations and combinations and how they work with the multiplication principle. In our next lesson, we're going to take what we've learned now about counting intelligently with permutations and combinations, and we're going to start talking about probability. But before I close this lesson, let me just mention this. If you find this information on permutations and combinations interesting, let me suggest to you that you continue studying this topic further. There's a lot you can find on this kind of thing. And one of the things you can find is a course by Art Benjamin for the teaching company called Discrete Mathematics. You might want to actually look that course up. Art's a wonderful colleague of mine and a fabulous teacher. I'll see you next time as we talk about probability.